Hi, welcome to our 8th training session, where we will demonstrate how to combine and configure two general-purpose I/O pin, one as an analog output, and another as an ADC input. We will then write an ISR handler for ADC interrupt, read ADC conversion data, and display the analog DAC voltage on LCD. Any embedded system project involves three important steps. The first step, we select embedded C as our programming language. The second step, LPC 2148 based evaluation board, and the LCD module to display voltage reading. Programs written in C are readable and easy to debug. To debug embedded C program on the PC, we use a simulator. We use a Jaguar debugger to download and test the program running on the target hardware. Throughout this course, we use general-purpose I/O to interact with the outside world. Since the real world is analog, but the computer world is binary, we need devices to convert signals between the two. Devices that change an analog signal to a digital signal are called analog-to-digital converters or ADC. Devices that change a digital signal to analog are called digital-to-analog converters, or DAC. A 1-bit embedded system can have only two values, 0 and 1. While an 8-bit system has the ability to detect 256 analog levels. LPC 2148 has a 10-bit ADC and DAC, and has a precision of 1 part in 1,000. All C programs starts from main. In our first function call, we initialize general-purpose port pins. We configure first 16 pins of port 0 as output. In the second function call, we initialize timer 0, and generate timer interrupt every 1 millisecond. In the third function call, we initialize the LCD module. First 8 pins drives LCD data bus, while next 8 pins are for control application. In the fourth function call, initialize DAC, we configure the multifunction port pin P0.25 for digital to analog conversion. While in the fifth function call, port pin P0.21 is configured for analog to digital conversion. We then use a flying leads to complete an analog loop back between DAC and ADC. We then start ADC conversion by clearing the ADC interrupt flag and enter a while one loop. In this unending loop, we check for ADC interrupt by reading ADC interrupt flag. If this flag is set, it indicates ADC conversion is over. We read ADC data register and display the value as voltage on the LCD module. We then increments a 10-bit counter and outputs this digital count value to the DAC. The second function initializes the timer for generating 1 microsecond interrupt. As the CPU clock is 16 MHz, the default peripheral clock will be 4 MHz. We generate a 1 microsecond interrupt by programming the match register AMR0. The crossware wizard computes the values to be loaded into the AMR0 register and generates the code for resetting the timer counter and also generating timer interrupt. The vector interrupt controller is programmed with slot 0 for timer 0 interrupt and the vector address pointing to timer interrupt subroutine. The third function initializes the LCD module. We first create an command array named CMD8 which has all the commands written to the LCD controller. The LCD pointer is initialized to the first location in the command array. The pointer is incremented until the end of array is reached. The register ISET is loaded with command data, and then the enable pin E is toggled to strobed the command data into the LCD module. These commands resets the LCD module and configures the module to operate in 8-bit mode with 2 lines of display. In the initialize DAC function call, we need to configure the multifunction pin P0.25 as digital to analog converter. If pin 18 and 19 are both 0, it behaves as a general purpose I/O pin, but if pin 18 is 0 and pin 19 is 1, then it is configured as digital to analog converter. In the fifth function call, we configure the multifunction pin P0.21 as analog to digital converter. If pin select 1 bit 10 and 11 are both 0, it behaves as a general purpose I/O pin, but if pin 10 is 0 and pin 11 is 1, then it is configured as analog to digital converter. LPC 2148 ADC1 has 8 analog input channels. ADC control registers, bits 0 through 7, allows one of the 8 channels to be selected for analog to digital conversion. We select channel 6. The ADC interrupt enable register, bits 0 through 7, when set, identifies those ADC channels, which are responsible for interrupt generation. In this case, we select the 6th channel. The next step is to program the vector interrupt controller. We enable ADC interrupt by setting bit 21 high in interrupt enable register. Select the ADC interrupt for IRQ mode of interrupt. Reserve slot number 2 for both vector interrupt control and vector address. The vector address 2 points to ADC interrupt ISR. The start ADC function call has dual job. The first job is to output digital data to the DAC register. The second job is to start conversion by setting bit 24 high in ADC control register. This operation starts ADC conversion immediately. We will read the ADC converter when the conversion is over, which will be signaled by an interrupt. Hence the ADC interrupt flag is reset to 0. In the timer interrupt subroutine, we very well know the time interval is 1 millisecond. Hence we decrement all time-dependent variables. We enable timer for the next 1 microsecond interrupt by clearing the match interrupt flag set in the IR register. Similarly, we signal the VIC end of timer routine by a dummy write to the vector address register. The execution of ADC ISR indicates the ADC conversion is over. The ADC data is available, ADC data register. As the ADC is 10 bits, the data is made available from bit number 6 through 14. We need to shift the data and compute external voltage value by defining the ADC voltage range and 1024-bit resolution. As the reference voltage is 3.3 volts, we have a resolution of 3.3 millivolts. We clear ADC1 interrupt flag and do a dummy VIC write to signal end of ADC ISR. The ADC interrupt flag variable is set to 1. The getADC function is called after ADC interrupt, and we need to convert the analog voltage to a decimal form. Hence the function hex to decimal is called for. This decimal value of the analog voltage is then converted to ASCII and punched into the message array. The message pointer is initialized for displaying the ASCII voltage data on the LCD module. The home cursor function call is a command to the LCD module. The home command instruction code has a value 2, and this value is driven on the data bus. The LCD control bit E is then toggled high and then low for strobing this command into the LCD module. The last function call, show message, displays the analog voltage reading on the LCD module. The LCD module has two 8-bit registers, one for command, and one for data. The ASCII data, pointed by the message pointer, is made available on the first 8-bit of the port 0. By setting the register select pin, high, the data register is selected, for strobing ASCII data to LCD display module. The enable pin EE is then toggled high to low, which strobes the ASCII data to LCD module, for display. The message pointer is incremented, until it hits end of message array. This process of reading ADC input and then displaying ASCII voltage value on the LCD module is an unending process,